In this lecture, we continue studying functional learning. I'm going to introduce a simple but very effective method. The basic idea is to pre-train a neural network on large-scale data, and then perform fine-tuning on the small support set. Despite its simplicity, the accuracy is comparable to the state-of-the-art. Let's first revisit some math basics. Cosine similarity can measure how similar two vectors are. In this example, there are two vectors, x and w. They have unit length, that is, their L2 norms are equal to 1. I plot x and w as the blue and red arrows in the figure. Let theta be the angle between x and w. In this example, x and w are unit vectors. Thus, cosine theta is equal to the inner product of x and w. Cosine theta can measure the similarity between x and w. Cosine similarity can be understood in this way. Project vector x onto the line spanned by w. The length of the projection is a cosine similarity. The length is between -1 and +1. If x and w are not unit vectors, we can normalize them to unit vectors before computing the cosine similarity. Cosine similarity is computed using this equation. We normalize x and w respectively and then compute their inner product. The inner product is the cosine similarity. Let's revisit Softmax function. It is a very commonly used activation function that maps a vector to a probability distribution. The input is phi. It's a k-dimensional vector. Denote its elements by phi sub 1, phi sub 2, dots, phi sub k. Softmax applies exponential function to all the k elements of phi to get k positive numbers. Then normalize the numbers so that they add up to 1. The k numbers are the outputs of the Softmax function. Denote the k numbers by vector p. Let p be the output of Softmax. The elements of p add up to 1. Here are some properties of Softmax. Its input and output are both k-dimensional vectors. The elements of the output vector p are all positive, and their sum is 1. Thus, p is a probability distribution. Softmax is typically applied upon the output of a multi-class classifier. If there are k-classes, then the output of Softmax is a distribution over the k-classes. Here is an example of Softmax function. The left figure shows the inputs. The inputs can be arbitrary numbers. The right figure shows the outputs. The outputs are positive numbers that add up to 1. Softmax function makes the biggest entry bigger and the other entries smaller. Why is the function called Softmax? If we use a max function, then the biggest entry is mapped to 1, and all the other entries are mapped to zeros. Softmax makes the biggest bigger and the others smaller, which is similar to the max function. But Softmax is more gentle than max. Softmax does not make the biggest as big as 1 and the others as small as 0. Softmax classifier is made of a dense layer and a Softmax activation. The input of the classifier is the feature vector x. Apply X to the parameter matrix W, and then add vector B. Finally, apply the Softmax function. The output is vector P. If the number of classes is k, then vector P is k-dimensional. Matrix W and vector B are the trainable parameters of the Softmax classifier. They can be learned from training data. Matrix W has k rows. K is a number of classes. Every row of W corresponds to a class. Most few-shot methods are based on very similar ideas. They use a large-scale dataset to pre-train a neural network, which will be used for extracting feature vectors. When making few-shot predictions, we can use a pre-trained neural network to map images to feature vectors. Then we can compare the query image with the images in the support set. For example, we can compute their pairwise cosine similarity. Finally, use the similarity scores to make predictions. I listed 2 papers in below. You can read the papers for more details. Let's build a convolutional neural network for feature extraction. The neural network has convolutional layers, pooling layers, and a flattened layer. Perhaps it has several dense layers. The input is an image. The output is a feature vector. Denote the input image by x and the output feature vector by f of x. The neural network can be trained in different ways. For example, it can be trained using standard supervised learning. It can also be trained using the Siamese network. The way of training will affect the final prediction accuracy. Different ways of training will have different prediction accuracies. Now I'm going to introduce a few-shot prediction method. This method and its variants are used in many papers. In this example, the support set is 3 with 2-shot. There are 3 classes: squirrel, bulldog, and puffin. Each class has 2 samples. Apply the neural network F to extract features. Each image is mapped to a feature vector. In this example, each class has 2 samples and thereby 2 feature vectors. Average the 2 feature vectors of squirrels to get a mean vector. The obtained mean vector is the representation of the squirrel class. The support set has 3 classes, so we got 3 mean vectors. They are the representations of the 3 classes. Then normalize the 3 mean vectors to make them have unit length. Denote the unit vectors by mu1, mu2, and mu3. Each mu vector is an embedding of a class into the Euclidean space. When making few-shot predictions, we will compare the query with the mu vectors. Now, we are ready to make few-shot predictions. Given the query image, we use the pre-trained model to predict what the query is: squirrel, bulldog, or puffin. We use the pre-trained neural network F for feature extraction. The query image is mapped to a feature vector. Then normalize the feature vector so that it has unit length. Let Q be the resulting unit vector. We have mapped the support set to 3 vectors. They are mu1, mu2, and mu3. They are unit vectors. Each mu vector represents a class. mu1 represents squirrel. mu2 represents bulldog. And mu3 represents puffin. Let matrix M be the stack of the 3 mu vectors. mu sub 1, mu sub 2, and mu sub 3 are the rows of matrix M. Now, let's make a prediction. Multiply matrix M by feature vector Q. Then apply the softmax function and obtain the output vector P. P is a probability distribution over the three classes. With P at hand, we know to which class the query belongs. We know also how likely the query belongs to each class. This is actually the softmax classifier. We treat vector Q as the feature vector and matrix M as the parameter matrix. The classifier can tell us to which class the query Q belongs. The matrix M has three rows, mu sub 1, mu sub 2, and mu sub 3. Thus, the product of M with Q is the three-dimensional vector. Its entries are the inner products of Q with mu sub 1, mu sub 2, and mu sub 3, respectively. Think of this question. In this example, the vector P has three entries. Which of the three entries is the biggest? Obviously, the first is the biggest. The inner product of Q and mu sub 1 is the biggest among the three inner products. So the first element of P is the biggest in P. The model believes the query image belongs to the first class, that is squirrels. We have used the pretrained model to make few-shot predictions. We can in addition perform fine-tuning after the pretraining. Recent papers demonstrated that fine-tuning can improve the prediction accuracy. Here I list several papers that use fine-tuning. They are motivated by very similar ideas, and they use similar methods. Let's revisit few-shot prediction using pretrained CNN. Let X sub j, Y sub j be the j sample in the support set. X sub j is an image, and Y sub j is the label. Denote the pretrained CNN by function f. It can map an image X to a feature vector. Taking the feature vector f of X sub j as input, the softmax classifier outputs a probability distribution P sub j. Assume the support set has three classes. Then the matrix W has three rows, and the output vector P sub j is three-dimensional. The three entries of P sub j are the probability or confidence scores of the three classes. Previously, we didn't use fine-tuning. We simply fixed W and B instead of learning them from data. We set W to M and B to the O0 vector. Recall that the rows of matrix M are the mean vectors of each class. If the support set has three classes, then there are three mean vectors, mu sub 1, mu sub 2, and mu sub 3. Each mean vector corresponds to a class of the support set. Setting the parameter matrix W to matrix M, then the output of the softmax classifier is three-dimensional. The three entries of P sub j are the similarities between the query and mu sub 1, mu sub 2, and mu sub 3, respectively. Previously, we used fixed parameters W and B without learning them from data. Alternatively, we can learn W and B from the support set. This is known as fine-tuning. Many recent papers show that fine-tuning can substantially improve prediction accuracy. The parameters W and B can be learned in this way. Use cross-entropy to measure the difference between the target Y sub j and the prediction P sub j. The cross-entropy is a loss. The support set has a few labeled images. Every image corresponds to a cross-entropy loss. Use the sum of the cross-entropy losses as the objective function. That is to say, we use all the samples in the support set to fine-tune the model parameters. The minimization encourages the prediction P sub j to approach the ground truth Y sub j. The minimization is taken with respect to the parameters W and B. We seek to learn W and B from the support set. Optionally, we can update the convolutional neural network F during the fine-tuning. That is, let the gradient propagate to the convolutional layers so that the extracted features become more effective. The support set is typically small. It has at most tens or hundreds of samples. So we had better use regularization to alleviate overfitting. There are a variety of regularizations to choose from. A recent paper recommends entropy regularization, which I think very reasonable. I'm going to introduce the entropy regularization later in this lecture. Many papers empirically demonstrated that fine-tuning can substantially improve prediction accuracy. This ICLR 2020 paper concludes that fine-tuning leads to big improvements. For 5-way one-shot, the improvement is 2 to 7%. For 5-way 5-shot, the improvement is 1.5 to 4%. Several other papers have similar observations. Although the support set is small, using it for fine-tuning the classifier helps improve the prediction accuracy. Fine-tuning after pretraining is better than using pretraining alone. While the method of pretraining with fine-tuning is very simple, its performance is comparable to the state of the art. There are over 100 methods for few-shot learning. I cannot introduce every method. I choose to teach the method of pretraining with fine-tuning because it is simple and effective. When fine-tuning the model, we seek to train a softmax classifier on the support set. Matrix W and vector B are trainable parameters of the softmax classifier. A good initialization is very helpful, especially when the support set is small. Random initialization is not a good option. Instead of using random initialization, we can use matrix M to initialize W. Let's revisit matrix M. If the support set has 3 classes, then M has 3 rows. Each row of matrix M is the embedding of one class into the feature space. In this example, the 3 rows of M respectively correspond to squirrel, bulldog, and puffin. A softmax classifier is parameterized by matrix W and vector B. Previously, we fixed W to M and B to all zeros. This kind of setting works well in practice, so we can use this setting as the initialization. This is a very reasonable initialization. In sum, the first trick for fine-tuning is using M and B as the initial parameters of the softmax classifier. The second trick is using entropy regularization. Because the softmax classifier is trained on a small support set, overfitting can happen. A good regularization can alleviate overfitting. This paper recommends entropy regularization. I think it makes great sense. Let's study entropy regularization. Let X be a query image. We can use a pre-trained convolutional neural network F for feature extraction. Let f of x be the extracted feature vector. It is the input of the softmax classifier. Vector P is a prediction made by the Softmax classifier. P is a probability distribution. Each element of P is a probability or a confidence. We can measure the spread out of the distribution P using entropy. Here is the definition. P sub I is the ith element of vector P. Compute the sum of P sub I times log P sub I for all the elements of P. Then take the negation. Typically, there are multiple queries. Each query has such an entropy. We can take the average of all the entropies. The average is the entropy regularization. We wish to make the entropy small. I'm going to explain the reason. Assume a classification problem has 3 classes. So the Softmax classifier outputs 3 probabilities. The figures plot the probabilities. On the left, the 3 probabilities are almost the same. It means the classifier is confused. The classifier doesn't know what the query is. We don't like such a result. The figure on the right is another probability distribution. One probability is big, and the others are very small. It means the classifier is confident that the query belongs to the second class. This is what we hope to get. We like this result. On the left, the 3 probabilities are almost the same, so the entropy is big. We don't like this kind of outcome, so we don't like big entropy. On the right, the probability density is concentrated in the second class. We hope to get such an outcome. In this case, the entropy is low. That's why we want to minimize the entropy regularization. The third trick is to combine cosine similarity with Softmax classifier. According to some recent papers, this trick can substantially improve classification accuracy. I think you are already familiar with the Softmax classifier. The Softmax classifier takes a feature vector Q as input. Compute W times Q plus B. Then apply the Softmax function. The outcome is probability distribution P. W times Q plus B is such a vector. If matrix W has 3 rows, then this vector is 3-dimensional. Its entries are W1 times Q plus B1, W2 times Q plus B2, and W3 times Q plus B3. We can replace the inner product of W and Q by their cosine similarity. Cosine similarity is actually the inner product after normalization. We normalize W and Q by dividing them by their L2 norms, respectively. With the inner products of W's and Q replaced by cosine similarities, the Softmax classifier becomes this one. The difference is very small, isn't it? The only difference is the normalization of W and Q before computing their inner product. According to the recently published papers, the small change can substantially improve accuracy. Let me summarize this lecture. The basic idea of feature learning is to pre-train a neural network for feature extraction. With such a neural network at hand, we can compare 2 images in the feature space and thereby make predictions. Feature learning typically works in 2 steps. First, pre-train a neural network on a big dataset. The network can be trained using standard supervised learning, triplet loss, or whatever method. The pre-trained neural network can extract features from images. The second step is making few-shot predictions. Given a query and a support set, the model needs to predict which class the query belongs to. We can map the images in the support set to feature vectors, then average the feature vectors in the same class to obtain a mean vector, mu. If the support set has k classes, then we will get k mean vectors, mu sub 1 to mu sub k. We compare the query's feature vector with the mu vectors to find their cosine similarity scores. Prediction can be made based on the similarity scores. Pre-training followed by few-shot prediction is the simplest approach. We can additionally add fine-tuning between the two steps. Experiments show that fine-tuning can much improve the prediction accuracy. After pre-training, we can fine-tune the model using the support set. The support set has labeled images. We can use them to train a softmax classifier. We can further fine-tune the convolutional neural network so that the extracted features are more effective. I have introduced 3 useful tricks for fine-tuning. First, don't randomly initialize the softmax classifier. Instead, use matrix M to initialize parameter matrix W. The rows of M are the mean vectors, mu's. Second, use the entropy regularization to alleviate overfitting. Third, combine the cosine similarity with the softmax classifier. Using cosine similarity to replace the inner product sounds almost trivial, but it does improve the prediction accuracy. I have finished this lecture. Thank you for watching. The link to my slides can be found below the video.